We have a single bolted double cover butt joint. It is used to connect two plates which are 8 mm thick. Okay. The plates then we have 16 mm diameter bolt. The grease of the bolt is 4.6, just like we have been using. Cover plates are 6 mm thick. Okay. Now what we have to do, we have to calculate the strength and efficiency of the joint. Earlier we were calculating the strength of the connection, strength of the bolt. Now we have to calculate the efficiency of the joint also. The 4 bolts are provided in the single bolt line at a pitch of 45 mm. Okay. And again, we have to determine the efficiency. 2 lines of bolts are provided, like here. Okay. In one case, what we are doing, we are asked to provide bolts in a single line, 4 bolts this way, another 4 bolts will be here on the other side. And in case we are providing them in 2 lines, so there will be 2 and 2 bolts. Okay, so this is our sectional view. So this way we are providing the bolts case A and case B, and we have to find the strength and the efficiency of both these 2 joints. Okay, the thickness of the plates are given. These are main plate that are being joined. The diameter of the bolt is given. Grade of the bolt is given. That will give us the ultimate strength and tensile yield strength. Then cover plate given, and the pitch has already been mentioned, 45 mm. Now almost same. Now we know already these things. If it is 410 plate, then the ultimate tensile strength of the plate is 410 megapascal or Newton per millimeter square. If the bolt is of grade 4.6, then the ultimate strength of the bolt material is 400 megapascal or Newton per mm square. Factor of safety we know already from table 5 of IS 456, sorry, IS 800. 1.25, that is the partial safety factor for the material of the bolt. From where we are getting it? IS 800, table number 5. Then we have to find out the net tensile area of the bolt. Just like we did in earlier case, also here, 78% of the gross cross-sectional area. How much is the gross cross-sectional area? Pi by 4 d square, d being 16 mm. So that value is the gross cross-sectional area, obviously. That will be multiplied with 0.78, and we will get the net tensile area of the bolt. Now the bolts will be in double shear. Now for calculation of the thickness, okay, for calculation in the formula, we have to provide one term, one value of thickness. Now what the thickness will be? It is going to be the list of aggregate thickness of cover plates. That we have to add the thickness of the cover plates and the minimum thickness of the main plate. Okay, so if it is single cover, thickness will be 8 mm. If it is double cover, it will be different. So first case, strength of the bolt in shear per pitch length. Okay. So this is a pitch length, right? This way. So we are finding out the strength of the bolt per pitch length. This is 45 mm. What is pitch length? From one bolt to another bolt, this is all 45 meter. Or we can say here also equal distance to the midpoint, mid region of the 2 bolts to the mid region on the other side. It is going to be the pitch length. This is 45 mm. Or this value, this is also 45 mm. and this is eighth distance. We will come it later. We have this bolt line here. From here to the eighth of the that is eighth distance. What is that value? 1.7 times of the hole diameter. That will give us the eighth distance. So same formula that we have been using, that same formula that we have been using from IS 800 clause number 10.3.3, that same formula is to be used, but we have to multiply it by 2, because in this case we are finding out the strength of the joint, and in this joint per pitch length we have how many bolts? We have 2 bolts. Okay, we're not talking about 1 bolt only now. We're talking about the joint per pitch length. Okay, so this is the pitch length, per pitch length of the joint. So here we have 2 bolt, therefore we are multiplying the value for a single bolt by 2. As simple as that. So this is the formula. We know all the values. 400 is the ultimate strength of the bolt. This is the net tensile area. Then we have root over 3 in the formula, and then we have the factor of safety of 1.25. So this comes out to be 58 kilonewton, right? So if this is a bolt, so these are the threaded portions. Obviously, when it is a threaded portion, the net area reduces to some extent. Okay, so that is why we have to multiply these factors. And this is the shank, this is head. We know these things, right? This will be called the threaded portion, the threaded length. Then the other portion is the grip length, which will be holding. We cannot use the nut there, right? Obviously, simple things. We know these things already. Then just see here. So here we have 2 plates, 2 cover plates, and these are the main plate. So the bolt, there are some clearance in the hole, because if it is 16 mm diameter, what is the hole diameter? It's 18 mm, right? So there is a clearance little bit. And then where we will have the shearing action, we will have the shearing action here. In this region, we will have this shearing action. In this region, we will have the shearing action. Okay, so these are the region of shearing action. And then here, at these places, the action of the bolt on the plates, these are the bearing. Okay, so these are the bearing stress here at this point. Okay, these are the bearing stress. Then after finding out the strength in shear, we have to go for finding out the strength of the bolt in bearing per pitch length. Now here, the formula is the same, that one that we have been using in last class also, clause 10.3.4 of IS 800. What is KB? KB we have to find. KB is the least of these factors. E naught divided by 3D naught, P divided by 3D naught minus 0.25, FUB divided by FU and 1. All this we have to find out, and whatever is the minimum value of these factors will be the value of KB. So what do we do here? E naught. E naught is the eighth distance. Now that was not given to us. 1.7 multiplied by D naught. Okay. If the bolt is 16 mm diameter, the hole will be 18 mm diameter. So we multiply it with 1.7. We will get the eighth distance. It is 30.6, but 30 can be taken. Then we have these 3 and D naught. D naught is the hole diameter. Now we know these things already. From where we are getting this? Table number 19 of IS 800 that talks about the diameter of the bolt and of the hole, the clearances that we should consider in the connections. So we got one factor here. Then we have another P divided by 3D naught minus 0.25. What is P? P is the pitch distance that is already provided. 45 mm divided by 3 into 18 minus 0.25 comes out to be 0.58. Then we have another factor FUB, that is the ultimate strength of the bolt divided by ultimate strength of the plate. So 400 divided by 410, this is going to be 0.975 and then 1. So what is the minimum? Obviously 0.55. So AB will be 0.55. Then we go to the formula. Same formula, 2.5. We have KB. We have the diameter of the bolt. We have thickness. That is the thickness of the main plate, 8 mm. Then ultimate strength of the plate, and then the factor of safety 1.25. So it comes out to be 57.73 kilonewton. This value will come in Newton, and that is to be converted into kilonewton. Then net tensile strength of the plate per pitch length. Okay, now we haven't used this formula. So this is another formula. Here we have 0.9 times Fu divided by gamma AN. What is AN? AN, this factor here, is the net tensile stress area as specified. There are holes in the plate. The plate is not like before. It has holes for the bolt. So therefore, we have to consider the net area. We cannot take the gross area. Then gamma M1 is a partial safety factor, which is 1.25. Again, it is from IS 800. Now in this formula, what we have to do? This is 0.9 is already there in the formula. Fu is 410. We know that the ultimate strength of plate 1.25 is the factor of safety. That is also known, right? Now what is happening here? We are taking the cross-sectional area. The cross-sectional area here, right? We are taking the cross-sectional area here. So it was 45 mm minus the diameter of the hole, that is 18 mm, and multiplied by the thickness. So if we look from this side, so the forces are being applied. The forces are being applied this way, right? Forces are this way. Therefore, we have to consider the section perpendicular or transverse to the forces being applied. So if we do that, if we look from this side, if this is our plate, this is per pitch length, let's say, this is 45 mm. This is the plate, this is some thickness, which is 8 mm. And then here we have a hole. Here we have a bolt, here we have a hole. This is 18 mm. So this is the net area, 45 minus 18 multiplied by the thickness. Okay, so these are simple things. Here, this one, 45 minus 18 is the net area remaining. 45 is the original pitch length. 18 mm is the hole diameter that is not there in the plate. Therefore, we are subtracting this and multiplied by the thickness of the plate. So that will give us the net tensile strength of the plate. Calculated the strength of the joint in shear per pitch length, then in bearing, again per pitch length. Now the formula is not changing because how many bolts are there, it is not a part of that factor in case of bearing. Then we are finding out what is the net tensile strength of the plate per pitch length. We have our formula known, that is 410 megapascal. Gamma M1, that is the factor of safety 1.25. That is also known. What will be the net area? The net area is like this. If this is our plate, we are considering only the pitch length 45 mm. We are considering, we have a bolt there. The diameter of the hole is 18 mm. So what is the net area? These are the net area, right? 45 minus This is 45. So 45 minus 18 multiplied by the thickness of the plate is our net area. On this net area, only the tensile force is acting through the plates. So therefore, this is 45 minus 18 multiplied by thickness. All other factors is known to us and we get the value in Newton converted into kilonewton. This is our strength of the plate per pitch length in net tension. Okay. Then these things are conditions when we have the bolted connections there. What if there were no holes? Okay, what if there were no holes in the plate? What would be the strength? There we have to find out to compare because we are supposed to find out the efficiency. Okay, the joint has increased or decreased the strength of the plate by how much? That is our idea to find out. Therefore, we have to find the strength of the plate when there were no holes, when it was a solid plate. So it's the same formula, but in this case, we will be using the pitch length because there are no holes now. We do not have any concept of net area. The entire area is now acting. There are no bolt holes, right? So it is 45 mm multiplied by 8 mm. This is the total area. All other factors remaining same. We get this much Newton converted into kilonewton. Okay, this would have been the strength of the plate if there were no bolts, if there were no connections. So now we will compare this value with the other values that we have obtained. Now, what will be the tensile strength of the joint per pitch length? It will be obviously the least. We have checked for different conditions and which one we shall be considering for our design purpose, the least one, because the external force, if the external force reaches the least value, it is going to fail, right? So therefore, the minimum value will be considered in shear, bearing, and net strength of the plate. So it comes out to be 57.73 kilonewton, the minimum of all the three conditions that we have checked. Then what will be the efficiency? This 57.73 divided by the force that we got when there were no holes. If there are no holes, in case of the solid plate, this is the strength and this is the minimum of the all the three conditions. So this is the efficiency of the joint. With the joint, with the connections of the bolt, we get only 54.32% of the strength that we would have got if there were only the solid plate. Okay. Then there we have another condition when the bolts are arranged in two rows. So we did it for this condition. Then we have another condition, this one. Okay, if it is done in two rows like this. So for the values in shear, here we did, right? We had the formula for one bolt, we multiplied it with two bolts. Now we have four bolts here. So what we have to do, we will come here, we shall have to multiply that value by 2. Earlier it was 2, now it is 4, so the value will be double. So we come here, the value in shear and then the net tensile strength is this one. The minimum is obviously 63.76 kilonewton. So now this will be considered as the strength of the joint. We have already evaluated the strength